Hello, my name is Jeff Schulz, and welcome to Human in the Loop extension to stream classification for labeling of low altitude drone imagery. I'd like to thank my co-authors, Dr. Andrew Bruck, Dr. Derek Anderson, Dr. James Keller, Dr. Grant Scott, and Dr. Robert Luke III. So, before we get into everything, I want to talk a little bit more about my motivation. So, a couple of issues we want to try and tackle here in this presentation is the fact that traditional deep learning models are closed world. They only know what they're trained on. They can't use their knowledge to try and say, oh, I don't know what this class is. They usually force a classification. So the question we want to ask in our methods is, can we recognize a sample that belongs to an unknown class? Can we say, I don't know, instead of forcing a misclassification? The second issue we want to try and tackle is the fact that current labeling of deep learning datasets is very time and labor intensive. So can we use these concepts, active learning and self-supervised learning, to help improve the ease of labeling, specifically human-in-the-loop labeling? So first, let's look from a bird's eye view and say, what's human-in-the-loop labeling? So say you have aerial imagery or autonomous driving or surveillance system, and it's giving you a video stream, lots and lots of images, lots of data to process. Traditionally, your human operator is going to sift through that data manually and label it. Well, what if we had an algorithm that took care of a lot of that labeling for the human operator? So yeah, of course, the algorithm isn't going to be perfect. Some of those labels are going to be incorrect. It's going to probably miss some too. So for the most part, the human operator can just snooze and just monitor the algorithm and correct mistakes as necessary, lessening the load of the labeling on the human operator. So let's also tackle these two concepts, active and self-supervised learning, and how they pertain to this paper. So first off, active learning, basically just updating the knowledge of the system given user information. So in other words, online learning. So sometimes, as the model is progressing and training, sometimes they're learning through machine update or, labels, but sometimes it's also getting input from the human, and that helps it learn faster and more accurately as the training system goes along. And then on the second side, we got self-supervised learning, which basically just uses inherent information in the data to generate labels to train on. So this doesn't require any human input. But the idea here is when we combine these two things, we ideally have a system that can extend its knowledge given inherent features in the data, but ask for help when necessary. So let's talk a little bit more about how we combine these concepts with the human-in-the-loop labeling approach. So say we have these clear divisions of responsibility here in this flowchart between the human responsibilities and the responsibilities of the self-supervised algorithm. First, the human's going to provide training data to our algorithm. Our algorithm, the brains of it, is this novel algorithm called StreamSong. Now, StreamSong is a stream classifier that we'll talk about in the next slide, but it specializes on saying, I don't know. It develops a list of outliers of sample data if it determines not to be a part of the N classes that it was trained on. The human is also responsible for providing test data to stream on, whether that be aerial data or autonomous driving footage. Since StreamSong is a self-supervised algorithm, it provides a label guess given the inherent data, the feature data in the streaming data, and then updates the information inside, updates the knowledge of StreamSong given that label guess. And so StreamSong, being an online learner, will attempt to periodically cluster the outliers and try and find emergent patterns in the outliers. And if it does, it'll save that out as a new class, a new list of prototypes that we can now classify to with future incoming streaming data. Well, this self-supervised approach isn't going to solve every problem, so we need the active learning component, which is the user intervention interface. So every once in a while, the user can interrupt the stream and correct labels, or StreamSong may interrupt the process and ask the user for input on a specific problem, specifically usually naming a new class that it has found. So what is StreamSong? StreamSong is short for streaming soft neural gas. Naturally, this includes growing neural gas to establish class prototypes within the established patterns that the algorithm knows about. It also uses possibilistic k-nearest neighbor. Now, pknn is important here because pknn can give a typicality of 0 to all known classes if pknn doesn't think that this sample belongs to any unknown classes. This gives the algorithm the ability to say, I don't know what class this is. StreamSong also implements possibilistic c-means clustering. This is the clustering that is used on the outlier list to try and find emergent patterns. So the brains of streamsong is shown in this equation. This is the prototype's update equation. This is if streamsong has determined that a sample belongs to a known class, it uses this equation to squeeze or pull the prototypes in space to account for that new sample that it says belongs in that class. So what is streamsong doing from a high level? First, it requires initialization of training data of n classes. Streamsong then builds growing neural gas prototypes from each class and then uses those to build the class prototypes. This is the knowledge of the system upon initialization. Streamsong then uses that knowledge to then operate on the streaming data. So from the streaming data, from each sample, we'll get regions of interest. We'll throw each of those through pKNN to determine typicality to any of the known classes in the system. If pKNN says that the sample belongs in one of the n classes, the n known classes, then we use the class update prototypes equation that we showed in the last slide to stretch or pull the prototypes in space to update for that new sample. And then we move on to the next chip. We haven't found any new classes. We've just been updating the ones we know. If pKNN says this data point is an outlier, it doesn't belong to any of the known classes, then we will update the outlier list and periodically use PCM to cluster those outliers to try and find emergent patterns. If no emergent patterns are found, then we move on to the next chip. We just update the outlier list. But if a cluster exists, a pattern emerges in the outlier list, then we take those points out, we run growing neural gas on those points to establish the class pattern in space, and then we add that to the system to increase the knowledge. And now with future streaming data, we can classify with that new class. So that's the self-supervised approach, but now we need to extend streamsong with active learning for our human-in-the-loop approach. So how are we going to do that? First, we need to allow for the algorithm to interrupt the data stream upon emergent class detection and allow for the human to select which images provide the truth and provide a label for that new class. We also want to allow the human operator to interrupt at any time and correct misclassifications and improve the knowledge of the system. So what's that going to look like? We first have our input data, we generate our regions of interest, we put this data into streamsong, it iterates. Upon finding a new class or human intervention, we pop up a user interface that allows the user to select images and correct their labels at any time. So what is the user interface that the human will be watching while the data streams in? First off, we want to establish regions of the screen that streaming data will be streaming in, specific to each class that streamsong says it is. So each of these regions will be human, car, bush, etc. We also want a side panel, a region of the screen that populates for outliers, for images and chips that streamsong has determined to be not part of any of the known classes. And then for user controls, we want to allow the user to specify a data stream rate or pause the stream at any time and move forwards and backwards as needed, either to traverse through the data themselves or to go back and fix a mislabel if necessary. So here's a demonstration real quick, an animation that shows what the streaming data will do and how it will populate the user interface as the stream works. So you can see that chips are being classified and thrown into their regions of the screen that matches their classification, as well as this outlier side panel that's being populated for outliers. Now that we've discussed how we extend streamsong with active and self-supervised learning for a human-in-the-loop labeling approach, let's talk about some of the use cases we expect this approach to handle. So first off, let's talk about our data. Our data for this paper, we generated in Unreal Engine with the neighborhood pack. We simulated low-altitude drone flight through the scene with a camera to generate video streams. Ideally, we would then push this raw streaming data through a localization algorithm or change detection algorithm to get our regions of interest chips out. But we just manually chipped out the data in the labeling program VOT for use in this paper. These chips are as follows. Some of these chips are in this slide, including our known imagery, like humans, cars, benches, and bushes, as well as noise chips like fire hydrants, toilets, trash, things we don't care about and that we want the algorithm to filter out. So the first use case we want our human-in-the-loop labeling approach to handle is when our stream classifier identifies a new pattern. In this case, we want the stream classifier to pause the system and prompt the user for an input on that emergent pattern. So that includes selecting the similar images that belong in its emergent class and giving it a label. So we demonstrate this with the prototype in Python developed in Windows. Here's what that prototype looks like. So we have our regions of known classes where images stream into, as well as our outliers panel. When StreamSong identifies a new emergent class, this dialog box pops up. Now the user is responsible for selecting the similar images that belong to this emergent pattern and giving it a name. When the user adds this class, it adds to the knowledge of the system, and the UI updates to show now that we can stream into 3 known classes as well as continue to stream into our outliers. Now in our preliminary results, we see that this reduced image feature data doesn't cluster well in space, and therefore StreamSong doesn't usually find these emergent patterns very quickly. It usually takes a lot of data. So how do we reduce the load on the human operator and in waiting for these classes to emerge? Well, that's use case 2. In use case 2, we want the user to identify a new pattern. We want the user to preempt the identification of emergent pattern in StreamSong. So in order to do this, the user can pause the stream and correct any mislabeled data at any time. But we also want to make this streamlined and efficient. So when this happens, when the user clicks on an image to correct its label, the dialog box will appear that shows the image the user clicked and 9 similar images in space, so the user can batch edit. The user will select all the images that match the correction the user wants to make, provide a label for the class, and update it. Now that the system is updated with this information, hopefully we're making smarter, quicker decisions on the classifications of streaming data. But neither of these use cases really reduce the labeling load throughput on the user. So we want something maybe to extend and bootstrap StreamSong and provide correct labels that we can trust. We can do this by extending the existing algorithm with a seasoned object recognition algorithm like YOLO v5. YOLO v5 has shown in many results, many tests, that it can identify a lot of these easy chips, like people, trucks, cars, that StreamSong is missing and determining to be outliers. If StreamSong gets the input from YOLO that these labels are above a certain confidence value, StreamSong can then just take that as truth, not burden the user with those chips and labels, and then continue on and build the knowledge in the background. So basically we were just replacing, we were just supplementing the self-supervision of the algorithm with a seasoned object recognition algorithm like YOLO. So ideally, this reduces the labeling load on the human much further by taking a lot of these images out that YOLO is seeing, and then we don't have to burden the user with those images. They don't even show up on the user interface. So all in all, in this presentation, we showed how we can extend StreamSong for use in an active and self-supervised labeling workflow. And preliminary results show that StreamSong can find emergent patterns, just maybe not very quickly, especially with reduced image feature data. We also propose a human-in-the-loop user interface and ideas and discussions behind things that we want to see in a user interface for human-in-the-loop labeling. And hopefully this spurs discussion on future designs and considerations. For future work, we want to put elements of StreamSong under a microscope. We know that algorithms like pKNN have issues dealing with reduced image feature data in space. So we want to try and find alternate approaches to how we can stream classify this data. We also want to flesh out a full human-in-the-loop interface, considering human factors like cognitive ergonomics, to further reduce the load on the human operator even further. So in this presentation, we've discussed how to extend closed-world algorithms for open-world problems, and we've also proposed many ideas and considerations behind how to build an efficient human-in-the-loop labeling algorithm and user interface. So with that, thank you for watching. If you have any questions, put them on this page and I will get to them as soon as possible. Thank you.